In this video, we're going to discuss first-order vectorial ODEs that are linear. By vectorial, we mean that they will have their values in Rd. D will be the dimension of the space, but they will be first order, which means that there will be only one derivative. Now, before we start dealing with these equations, I need to introduce a definition, the exponential of a matrix. So let me choose a d by d matrix, square matrix of order d, and I will define the exponential of the matrix as the sum for k equals 0 to plus infinity of 1 over factorial k times a raised to power k. All these operations here are perfectly defined, and I will define the exponential of the matrix this way. Now, based on this definition, I can state a theorem, which is the Duhamel theorem, for all matrices A that are d by d, and for all vectors u naught, which is a vector of Rd, then the equation u prime equals au, which is a first order ODE with in dimension d, with the initial condition u of 0 equals u naught, will have a unique solution, and that unique solution will be u of t equals exponential ta times u naught. Now, I can get a little bit, I can actually be a little bit more general than what I just stated. I can also add a b of t, so it will be u prime of t equals a u of t plus b of t. And we still have the initial condition u of 0 equals u naught. Then this will have also a unique solution, which kind of starts the same way as before, exponential ta u naught. But I have an additional term, which is the integral between 0 and t of exponential t minus s a, the matrix A, times bs ds. Okay? So this is a way to solve, in a sense, our ODE, provided we can compute the exponential of the matrix, and also if we have a b of t, provided that we can compute that term here, the integral of that exponential. So the question is, how do you compute the exponential of a matrix? For instance, TA, or just for the sake of simplicity, let's take t equal 1 for now, just the exponential of a. Well, let me give you a little review of linear algebra. There exists a non-singular matrix P such that A can be written as P inverse a Jordan matrix J, P. Now, the Jordan matrix will be a diagonal matrix, which is basically zeros everywhere, but on the diagonal you have numbers which possibly are not 0, which will be the eigenvalue of A, plus n, which is a nilpotent matrix. That means that when you raise n to a certain power, at some point you will get 0. Okay? So if you write A in this form, in this way, then what you will have is that A raised to power k is P inverse JP, P inverse JP k times. So by simplifying the PP inverse, you will end up with P inverse JK times, so J raised to power k, times P, right? So now what you can say is that the exponential of A, or the exponential of TA, will be P inverse exponential of Tj P, or if t equal 1, then exponential A is P inverse exponential J P. And now what you can do is compute pretty easily, in a pretty easy way, exponential Tj, because it is a Jordan matrix, which is a sum of a diagonal matrix and a nilpotent matrix. So that will actually be way easier to compute the exponential of this matrix. And if you're not familiar with this, well, you need to review a little bit of linear algebra And here is a link to a video that I suggest you watch either now, you can stop the video, watch this other video and come back, or at the end of this class here today, just watch this video and make sure you understand how you can compute the exponential of a matrix. Now, I will use that now for an example. I will consider this ODE, y second minus 4y prime plus 3y equals 0, with y0 equals 2 and y prime of 0 equals 4. As you know from the previous video, this can be replaced by u prime equals au, with a equal to 0, 1, minus 3, 4. u0 is 2, 4, and u is y prime. Now, you want to find the eigenvalues of A, or basically you want to put A in a Jordan form. So you want to compute the eigenvalues of A. While you do this using the characteristic polynomial, while you find the solutions to your characteristic polynomials, which are 1 and 3. So here are your two eigenvalues. The spectrum of A, therefore, is 1, 3. These are the two eigenvalues of matrix A. Well, obviously, this matrix A can actually be put in a diagonal form, so it's even better than just a Jordan form, because at this point, n is equal to 0, so it's even easier. Now, the associated eigenvectors will be v1 and v2, 1, 1 for v1 and 1, 3 for v2. So my matrix P will be, actually the inverse of matrix P will be 1, 1, 1, 3. J, which will simply be a diagonal matrix, will be 1, 0, 0, 3. And P will be, well, the inverse of 1, 1, 1, 3. So that's basically 3 halves. Minus 1 half, minus 1 half, and 1 half. If you have any questions, it's not clear, well, I think that's very simple linear algebra, but in case of a problem, just put the video, stop the video for a few minutes, make sure you understand all of this, and then come back. Now, what we have is that A is equal to the inverse of P times J times P. So, well, in this case, it's going to be pretty easy to compute exponential Tj. Again, J is 1, 0, 0, 3, so Tj is T, 0, 0, 3, T. And, well, that's a diagonal matrix, so computing the exponential of this is very easy, because computing the power of J is very easy. So, exponential of Tj is exponential T, 0, 0, exponential 3t. Now, let me multiply by the inverse of P and P to the left and to the right. And, well, I just carry out the computation, and here's what I get. And again, you can stop the video and make sure that you are in agreement and you understand everything absolutely fully. Now, P inverse exponential Tj, P is known to be exponential Ta, right? So what I have is, based on Duhamel's theorem, what I have is U of t is exponential Ta times U of 0, which, when I just plug things in, well, exponential Ta is right above, and U of 0 is 2, 4, as we stated earlier. And again, U of t is Y of t, Y prime of t. So now let me just carry out the computation with this matrix and 2, 4. So I just multiply. There is no problem. And what I obtain is exponential t plus exponential 3t for the first component, and 3 exponential 3t plus exponential t for the second component. And of course, what I have at this point is the solution I was looking for. Okay? Now, what I'm saying is that, okay, we have a solution. The solution we have is basically the solution to this initial value problem, okay? And again, you can make sure that we did not make any mistake by plugging in this solution into the system and just verifying it works, right? You plug this in the ODE, it should work, and you verify that it also meets the initial condition. So there should not be any problem. Now, if we had not specified the initial condition, right? We did specify the initial condition. It was an IVP. But if we hadn't, if we had just dealt with the ODE and we had just left, you know, the initial condition as y of 0 and y prime of 0, then, well, instead of multiplying by 2, 4, I would have multiplied by y of 0 and y prime of 0, right? So as you can see, what I obtain is obviously an infinite number of solutions. It's basically a two-dimensional linear space. This is what I would get, right? Okay, now, let's say that I start with y of 0 equals 0 and y prime of 0 equals 0. Then obviously what I obtain is a solution, which will be a stationary solution, y of t equals 0. Okay, but what would happen if instead of having y of 0 equals 0 and y prime of 0 equals 0, they were not exactly 0, but very close to 0? This reminds us of a question we asked not so long ago, right? So let's ask this question again. Well, what would happen? Well, what would happen is that the solution would not stay close to 0. And the reason is the 1 and the 3, the exponential t and the exponential 3t. This is the reason why, obviously, if y of 0 is not 0 and y prime of 0 is not 0, then that will blow up, okay? So it will not stay close to the stationary solution. Now, what's interesting to do is to somehow trace these coefficients 1 and 3 to see where do they come from. Well, let's trace them. So remember the exponential TA, I mean the 1 and the 3 were basically there. I mean, I just put them in red so we can see where they come from. And as a reminder, this was coming from the diagonal matrix, Jordan matrix. I had a 1 and a 3, which in turn was coming from the spectrum of the matrix A. So what I'm saying is that if the eigenvalues of A, instead of being 1 and 3, if they had been negative, or if they had been complex but with a negative real part, then instead of having 1 and 3, I would have something, well, negative actually, possibly a complex number with a negative real part, and that means that these exponentials would converge to 0 when t goes to plus infinity. So what would happen is that the solution would come close to 0 rather than going away from it. So a corollary to the proposition we gave, to the Duhamel's theorem, is this one. If we have u prime equals au, and, well, if u of 0 is equal to 0, then obviously u of t is a stationary solution. That's not a problem. But if it's not equal to 0, then we have two situations. The first situation is all of the eigenvalues of A are negative, or at least if they're complex, the real part of these eigenvalues, of all of them, is negative. In this case, what happens is that u of t will converge to 0, in other words, will converge to the stationary solution as t goes to plus infinity. And by the way, we can even bound the norm of ut by u of 0 and the exponential of minus lambda t. Well, lambda will be the maximum, the largest eigenvalue of A with absolute values. Now, if, on the contrary, we have at least one eigenvalue, which is on the right-hand side of the plane, the complex plane. In other words, there is a real part of that eigenvalue which is positive. Well, in this case, we may find some initial u of 0 that will, the solution will not stay close to the stationary solution. Okay, and as a reminder, the set of eigenvalues is called the spectrum of A. It's denoted sigma A, and obviously this is what will drive the situation when it comes to linear ODEs, whether we will have a behavior of astability or of instability.